right, so welcome back, everybody. I hope that you had a chance to look at the video that I posted last night, uh, finishing up chapter 6, and that you've had an opportunity to look at your exponent rules. And you might want to pause this video right now and go grab your favorite calculator. It should have the ability to do roots. So if it's just like one of those like 4-function calculators, you're not going to be able to practice how to do these things, uh, on those calculators. If you have an iPhone, if you turn it off over to the side, the scientific calculator shows up there. So you could always do that because since obviously I'm not there to police what it is that you're doing and how you're getting these calculations. All right, so let's proceed. So we are going to be taking the roots of numbers, no longer just the square root. We'll take the 5th root, the 17th root. Obviously, that would be super tedious and pretty unlikely, but we'll hover around like the 4th or 5th root of these values for this lecture. And you can see here some pretty important definitions. Anytime you hear me reference the index, that would be whatever root we're taking. So the 5th root, the 10th root, that's your index. And if you don't see anything there, it's because we're taking the square root. You do not have to put a 2 over here if you're taking the square root, okay? This whole thing is called the radical. The stuff that's underneath the square root symbol, the radical symbol, sorry, is called the radicand, and then this is a radical symbol, all right? Radical symbol. So radicand, radical, index, radical symbol, okay? All right, so this is where having a calculator handy is going to be really to your benefit. So it really depends on what calculator, what brand you have, on how you're going to be able to type these in, the order that you're going to type them in. YouTube, let it be your friend on how to use your calculator that you're trying to use on how to enter these in the calculator. But you're generally looking for a button that either looks like this. So it'll be sort of like an X here, a square root symbol, and then maybe a Y on the inside. So that's a button that you could look for. Sometimes the X and Y are interchangeable. Sometimes the button looks like this. So it has like an empty box and then the square root. And then maybe sometimes like another empty box like this. So again, it really depends on what calculator you are using as to what button you are going to be looking for, okay? And without physically being there with you guys, normally what I would do in class is I would go to each student who didn't know how to input these in their calculator, and I would show you how to do it. Obviously, we don't have that luxury right now, but if you're having difficulties using your calculator to find these roots, just send me an email, and maybe we can set up a private Zoom or Blackboard Collaborate, whatever is easier for you, and I'll get to know what calculator you're using and show you how to use it, okay? So for now, let's take the 3rd root. That's how you would say this. So the cube root, or the 3rd root of 27, which is going to be 3. And we know that because the cube root is the inverse operation to cubing something. So if you were to take some value and raise it to the power of 3 to get 27, that value that you're raising to the power of 3 would be 3. So 3 to the 3rd power is 27, which is exactly why the cube root of 27 is going to be 3. All right, so the cube root here of 216 is going to be 6, and then the 4th root of 256 is going to be 4, okay? Without going into too much detail, because again, I'm assuming you're just banging this into the calculator and getting your results. And if you're not able to get those results, then you're going to have to send me an email so we can figure out how to use your calculator. Over here, the 5th root of 243 is 3. This one's a little bit interesting. What I would do, since we generally don't want decimal answers, is what you should be doing is you should be taking the 4th root of 16 and the 4th root of 81. This is actually going to be a rule that we're going to learn later in this class, that you can sort of divide and conquer. So you take the fourth root of 16, and then you take the fourth root of 81, and you get your, shiny answer of 2 and 3. So 2/3, 0.66666666, whatever. And this one over here, since you're given the decimal, you kind of have no choice but to write a decimal answer. So the third root of 0.064 is just 0.4. Okay. All right, so here's some rules for finding the principal roots. So if your index is even, so it says n is even, so index is your n. If it's even and a is a positive value or 0, then the nth root of a represents the principal nth root of a. And the opposite of the nth root of a represents the negative nth root of a, okay? Case 2 says if n is even and a is a negative, then this is not going to be a real number, because we cannot take the square root of a negative yet in this course. We can't take the fourth root of a negative. We can't take the 10th root of a negative, because it would be a non-real number. It would be an imaginary number, a complex number, which we haven't talked about yet. Okay, so for now, if n is an even number and your radicand is negative, then it's going to be a non-real number. Now, if your index is odd, it doesn't matter what your a value is, what your radicand is, we will be able to take that nth root of your radicand to get an answer, okay? And again, you'll just type that into your calculator to figure out what that result is. All right, so let's take a look at this. So again, this is the square root. So there's a 2 here, so your n is even. This is positive, so this is just going to be the square root of 36, which is, of course, 6. Over here, we want to work sort of backwards. We want to figure out what the square root of 36 is, and then we're going to take the opposite of it. So this answer is negative 6. The fourth root of 16 is just 2. The opposite of the fourth root of 16 is going to be negative 2. The fourth root of negative 16, now your n value is even and your radicand is negative. So this is non-real. And then over here, the fifth root of 243, we saw that one already. That is going to be 3. And then since your n is odd, it doesn't matter what this is. We could do it. It's not going to lead to a non-real number. This answer is going to be negative 3. And again, your calculator will give you that result if you are using it. Okay. So this is talking about radical expressions as an algebraic expression that contains a radical. So this is a square root function. We've actually seen this before in the class. I told you that this is what it looked like. We were talking about the domain of these functions way back in the day when we first introduced this. And the way that you figure out what that domain is again, you set your radicand, in this case is just x, you set it to be greater than or equal to 0, because you cannot take the square root of a negative number. So how do you avoid doing that? You say that your radicand, whatever is in there, has to be non-negative, aka greater than or equal to 0. And that's where this domain comes from. Okay. All right, so this is the cube function, cube root function, sorry. So this one, again, sort of allows for the negative, which is why it goes down underneath below the x-axis, where the square root function just is above that x-axis, because we cannot take the square root of a negative number. We're not allowed to get into the negatives when it's the square root. With the cube root, everything's fair game. All right, so the way that we graph this function, again, the first thing that we want to do is figure out what the domain is. So I'm going to go ahead and take a look at this. So I'm going to say x plus 2 is greater than or equal to 0. So we have x is going to be greater than or equal to negative 2. So these are the minimum values right here. This negative 2 is your minimum value, and then everything else is going to be bigger. So what I'm going to do to graph this function in the path of least resistance is create an XY table. We know that graphing is just a set of ordered pairs. So I'm going to set negative 2 to be my smallest value. I'll eventually substitute that in. And then I'm going to pick other values that are going to be interesting to me. So I'll pick negative 1 as another value. I will pick 2 as another value, and you'll see why I've chosen these values in a minute. And maybe one more for good luck. I'll choose, I don't know, 7. Doesn't really matter. You'll see that 7 goes off the grid, but we'll still do it anyway. So we're going to substitute these values in to this function. So we have the square root of -2 plus 2, which is the square root of 0, which is just 0. So when x is -2, y value is 0. So there's 1 point right there. Next one is going to be -1 plus 2, which is going to be the square root of 1, which is just 1. So the next point that we're going to have is -1, 1. So when x is -1, y is +1. The next one that I picked was 2. So plus 2 is equal to the square root of 4, which is 2. And I think you've hopefully have picked up why I picked these x values the way that I did, is I was trying to create perfect squares over here so I wouldn't have to graph a decimal value. So the next one we have when x is 2, y is 2. So there's another point right there. So 2, 2. And then again, last but not least, we have the 7 plus 2, which is the square root of 9, and that's 3. So 7, 3 would be the 4th point somewhere over here. All right, so we just kind of connect these guys together the best that you can, put an arrow right there, and now you have enough to figure out what the domain is. You know that your domain is going to be x is greater than -2, so domain is going to be from -2 to infinity. And then your range, you can pick up from your graph, you know that your minimum value is 0, and it's heading all the way to positive infinity as well, right? So there's example 3 on how to graph these radical functions and figure out the domain and range from the graph. Oops, sorry, I gotta get rid of this. All right. So this next slide here is pretty important because it just hammers down the fact that these are in fact inverse operations to one another, that they kind of cancel each other out, but they don't just cancel each other out. It also creates the absolute value as well, all right? And that just protects to see if there's a negative a value. When you square it, it becomes positive, and then you can take the square root of it. So that's why the absolute value is here. All right, so that's going to be critical for us to be able to do. Right, you'll see in a quick example of that in a second. So this says, according to the rule, it's the absolute value of whatever your a value is, which is just 15. So the absolute value of 15 is 15. Over here, it says the absolute value of -12. Again, -12 is our a value, and the absolute value of -12 is just positive 12. Over here, technically, you need the absolute value of y because you have no idea what this value of y is. It could be -14 for all we know. So we need those absolute value of y here. If it were me on a test, I would not require you to put that there. But because it's Math Lab and it's a computer system and it's pretty much going to make you put those there if it wants them, you're going to probably need to include those on the test when we eventually get there. Okay. And then last but not least, again, we need the absolute value of negative y, which is just going to be y here. Okay. There we go. All right, so over here, when n is an even positive integer, again, these sort of like cancel each other out, which is great. If n is odd, all right, then we don't have to worry about taking the absolute value because, again, we're allowed to have a negative number here if our index is odd. If it's even, then this has to be here. If it's odd, then you do not need the absolute value because, again, we're allowed to have negative results here. Okie dokie. So over here, when you're taking the 4th root of -5 to the 4th power, since your n is even, we do need the absolute value. So this is going to be +5. This time our index is up. This is odd. So we do not need the absolute value. So our result here is going to be -5. Over here, even, even. So this is going to be the absolute value of -3, which is 3. But then don't forget about this negative out front, and that's going to lead us to this -3 result here. This one is interesting because technically we don't know about this rule yet, but I'm going to show it to you anyway. The quick way to figure out what the fourth root of m to the 8th power is you can just take whatever this exponent is and divide it by your index. And that's going to leave us to m squared. All right. And of course, we know that we need to be the absolute value because our index is even. So we do need those absolute value there. And then, of course, we have this negative hanging out front. So we're going to put our negative in where it belongs. Over here, that same shortcut applies. Take this 24 and divide it by your index, which is 3. Since your index is odd, you do not need the absolute value. So you're just going to get x to the 8th power, because 24 divided by 3 is 8. And then last but not least, 18 divided by 6 is going to be y to the 3rd power, but your index is even, so you need the absolute value. Again, if this were me in my class and I was assessing you on a test and you forgot the absolute value bars, I would not take points off. But I cannot guarantee that MATLAB will let it slide. All right, so over here, this just says use a calculator to approximate the radical to 3 decimal places. So we're just going to go ahead and do these very quickly since they're calculator based anyway. So you just do 17 and then you just bang that into the square root here. And you should be expecting a value that's greater than 4 but less than 5, because the square root of 16 is 4, the square root of 25 is 5, so the square root of 17 has to be somewhere between there. And we got 4.123. All right, and then we got a 1 here, but of course we get rid of that because we're rounding to 3 decimal places. All right, this one is we're going to take the square root of 362. So 362, we're going to take the square root of that, and that's going to give us 19.026, and then we throw our negative in there as well. Okay, so hopefully you get the gist of these, of being able to put these in the calculator. If you wanted to know what the cube root of 9,482 is, iPhone calculator actually has a cube root button, which is pretty sweet. And we're just going to put that in as 21.166 because we have to round that up. Okay. So that is that. And I probably won't give you these on the test in MATLAB. They're just too basic. They're really like showing me that you can use a calculator, and that's just wonderful for someone. I don't really care. It's not part of algebra. All right, so 7.2, rational exponents. All right, so we're going to use exponential notation for nth roots. So we're going to be able to take these, radicals of, let's say, the 4th root of a, whatever that is. And we know that a, by our exponent rules, is really a to the 1st power. And we're going to be able to write this in exponential form, because it turns out that this radical is the exact same thing as having an exponent, which is a rational exponent. So your index is your denominator, your exponent here is going to be your numerator. And you're going to be able to take these, nth roots and write them in exponential form, and then use all of those exponent rules that we learned way back in the day. Right? We'll also define and use expressions in this form, convert between radicals and rational exponents, and then use the rules for exponents with rational exponents. Okay. All right, so here we go. So if we have the nth root of a is a real number, then a to the 1 over n is the same thing as the nth root of a, which is exactly what I just showed you. So hopefully that makes sense. Okay. Let's take a look here. So here we go. There's some examples here of the square root of 4, the 3rd root of 8. Again, it's 8 to the 1/3 power, all that good stuff. All right, so here we go. So we can evaluate this using our calculator. For those of you, again, it really depends on what calculator you have. You are either looking for a button that looks like this, so it has a caret, and that will allow you to raise this to the 1/5 power. If you're using this button, you generally need to open up parentheses, put 1 divided by 5, and then close those parentheses off in order to get what it is that you need out of this. Remember, your calculators are programmed to do PEMDAS. So if you say 32 raised to the power of 1 divided by 5, it's going to do 32 raised to the power of 1, which is 32, and then it's going to take 32 and divide it by 5. So you better make sure that you are raising it to the 1/5 power, not raising it to the first power, then dividing it by 5. So use parentheses appropriately. Some of you guys probably have a calculator that look like this, so it has a button that looks like that, which is nice. And use whatever calculator you have, use whatever button you're given, and then again, some of you probably have a calculator that has a button that looks like that. So again, it really depends on what calculator model you have, and if you're unsure of how to do any of this stuff, of course, just send me an email and we'll set it up so we can I can teach you how to use your calculator. So 32 raised to the 1/5 power is 2. 64 raised to the 1/2 power is 8. This, of course, is going to be 81 negative, and then 81 to the 1/4 power. So this is going to be -3 here. This one is a non-real. Since the negative is on the inside of the parentheses, that is the same thing, remember, as having the 4th root of -81. And since this is even and that is negative, that leads us to a non-real number. Where this one over here is equivalent to having the negative out front and having the 4th root of +81. That's what this one says. All right, so we got to be able to make sure that we're separating these two ideas. Okay, this is going to be -4, and this one, what I would do is sort of divide and conquer again. I'd have 1 to the 1/3 power, which is just 1, and then I'd have 27 to the 1/3 power, which is 3. So our answer is just 1/3. This is pretty neat over here as well. So again, I kind of indicated this earlier when we first introduced this, that your power for your radicand is going to be your numerator, okay? So the power of the radicand is going to be the numerator, and that will allow you to sort of still write it in exponential form, okay? All right, so we're going to evaluate a couple of these. Again, I'm not going to do every single one of these just because it's getting a little tedious, especially since it's just using your calculator. So what this says is when you have 25 raised to the 3/2 power, that is 125. And one way to sort of like check your answer if you're unsure is, again, you could visualize this in the radical form of being the square root of 25 raised to the power of 3. So the square root of 25 is 5 raised to the power of 3, and that is going to be 125. So that's the idea of how you're going to get 125, or of course, you're just going to type this into the calculator and get it. Again, over here, cube root of 27 is 3. 3 squared is 9, and that's all she wrote. Okay, we'll probably, like I said, we're only going to do a couple of these. Going back to your exponent rules, remember what happens when you have a negative exponent. So when you have a negative exponent, what that does is it pushes that base into the denominator. It doesn't change anything about the value of these exponents. It just tells us where the base is supposed to go. And if you're trying to remember what that means, there was a rule way back in the day that it said if it was x to the negative n power, that is the same thing as 1 over x to the n power. But now we are having a rational exponent, where this was just an integer exponent. Okay, we talked about that way back in the day. All right, so again, with this one, the first thing that I would do is I would use this negative exponent to say that this is 1 over 81 to the 3/4 power. And 81 to the 3/4 power is going to be 1 over, this should be 27. When you type in 81 to the 3/4 power in your calculator, that is what you get. Okay. Over here, again, deal with the negative exponent first. So 1 over 36 to the positive 3/2 power, and that's going to be 1 over 216. Okay. So again, you could do it this way, or you could just type it into the calculator, and you're going to get a decimal more than likely. And as long as you can convert that decimal to a fraction, you should be good. Okay. All right, so these are alternative meanings of these rational exponents. So you can pull the m out. These are all exponent rules. So you can put the m on the inside. Multiplication is commutative. Remember, when you have a power raised to a power, you are multiplying these powers together. So whether you have the 1 over n on the inside and the m on the outside, or the m on the inside and the 1 over n on the outside, it doesn't matter because multiplication is commutative. This is pretty neat as well, is that you can write it this way or you can write it this way. I've already written it once this way. If you go back to this problem right here, you can see that I wrote this as, the square root, and then I raised the whole thing to the power of 3. Most often I use this form right here. This is the one that's a little bit more visually appealing. I like to be able to write things without parentheses if I can, but this is a perfectly acceptable form of writing these answers. Okay. All right, so write the exponential as a radical, assume that all variables represent positive real numbers. And the reason why they said that is so we can abandon that whole absolute value business. So if you assume that the variables are positive, then you won't have to worry about taking the square root of negative or having the absolute value or anything like that. So this is the square root of 19. This one written as a radical is going to be the 4th root of 11 to the 3rd power. This is going to be 14 on the outside because, again, only the x is being raised to the 2/3 power. So this is going to be the cube root of x squared. This is going to be 5, and then the 5th root of x to the 3rd minus, now this whole piece is on the being raised to the power of 3/5. So this will be the 5th root of 2x raised to the power of 3. And you could always, distribute that 3. Remember, distributing quotes, right? So this would be, if you wanted to clean it up a little bit more, the 5th root of 8x to the 3rd. Okay. And then there's not much that we can do because we don't know about these rules yet. And then last but not least, since this is negative, we have 1 over. This will be the 7th root of x to the 5th. And, as you get comfortable with these, you'll be able to bang these out pretty quick as well. Just remember, the denominator is your index, the numerator is the power. That's the best way to try and remember these. Just write a bunch of these down and just practice it a few times. You'll get the hang of it pretty quick. Okay. These right here is just like a little bit of a reminder for all those rules of exponents that we learned a long time ago. When you have multiplying like bases, you add the exponents. When you have a negative exponent, it gets pushed down to the denominator. When you're dividing like bases, you subtract the exponents. When you have a negative exponent on the outside, you flip and then send it into both. Power raised to a power, multiply, sort of distribute, again in quotes, to both of these. So A and B are both getting that power of R. Again, sort of distributing this to both. A and B are getting the power of R. And then, last but not least, you have this A to the negative R. You could write it this way if you wanted to. Have to, but it's an option. Okay. All right, so one of the things that you want to think about when it comes to these rules, and I suppose I'll just go back to this real quick, is that, yeah, these rules are the same exact rules as before. Same rules. So when you're multiplying like bases, you add the exponents. Now your exponents are fractions. And we know that in order to add fractions, the only way that we can do that, or subtract fractions for that matter, is to have a common denominator. Okay? So that adds a whole new wrinkle to this, to the issue that you're doing, that you're experiencing when you're doing these problems. Is that you have to get a common denominator in order to add or subtract these fractions. All right, so let's take a quick look at this. So again, we know that we're multiplying like bases, so the base is going to be the same. We're supposed to add these exponents, so 1/2 plus 1/3. But we can't do that because we don't have a common denominator. So we need to do that. So we've got 3 is our base again. Our common denominator is 6. So that should be 3/6 plus 2/6, which is going to give us 3 to the 5/6 power. So again, in theory, it's as easy as it was before. When you're multiplying like bases, you add the exponents. But the problem is, you have to have a common denominator in order to be able to add these fractions. All right. Same deal here. So you have 7 to the 2/3 power minus 4/3, which is going to give us 7 to the negative 2/3 power. And we didn't have an issue with having a common denominator here, but we do have a negative exponent, and we need to fix that because there's a rule for that. And we will fix it by putting it into the denominator where it belongs. Okay. And over here, let's send that on in to everything on the inside here. So that's going to clean us up to be a squared. 6 divided by 3 is 2. 2 times 2 is 4. So b to the 4th over b to the 6th. And then we can simplify this one more time by saying it's a squared over b squared. Okie. All right, so this one's kind of neat because a lot of students look at this and they go, all right, well, I'll add these together first. Well, remember, you can't add these. You cannot add these. You don't add these exponents. You can't multiply these exponents. The only thing that you can do initially is distribute this in. So this r to the 2/5 power gets distributed in. And what that's going to do for us is it's going to give us r to the, let's see here, add that common denominator to the 5/5, because when you're multiplying like bases, you add the exponents. So 2/5 plus 3/5 is 5/5, or just r to the first power. And then over here, this is going to be r to the 10/5, which is just r squared. And that's it. I mean, I suppose you could, if you wanted to, factor an r out since we, spent time factoring those, but you obviously don't need to do that. It's not part of this. It just says write your answers with only positive exponents, which we've done. Okay. All right. So this is where the fun starts to happen here. So again, when you are multiplying these together, okay, one of the things that you need to think about is what these look like in exponential form. So I'm going to take these and I'm going to rewrite them so that they're in exponential form, and then hopefully that'll lead us down a path where we can easily get our answer. So in exponential form, this is going to be x to the 3/4 power. This is going to be x to the 1/5 power. And now we are multiplying like bases, which means we're supposed to add these exponents, but we can't do that until we have a common denominator. So this is going to be x to the 15/20, because that's the common denominator between 4 and 5 is 20. And this will be x to the 4/20, which will be x to the 19/20, which is an answer. But generally, you want to say leave your answers in exponential form. So that's good to go. If you wanted to, you could put this right back into radical form if you just prefer that one to be better. So you could write this as the 20th root of x to the 19th if you wanted to. Okay. And then we'll do this one. So again, x to the 2/5 power. Remember, this is not, sorry, this is, can't erase. So this is not a 1. I got so engulfed in the fact that this is not a 1, I switched them. So this is a 2 here. You know, the common error that students make is they think that this is a 1. So this is 5/1 is what they put. But the reality is it's 5/2, all right, divided by, again, x to the 1/3. And then when you're dividing like bases, you subtract the exponents. So you have x to the 5/2 minus 1/3. So you're subtracting those exponents, but you can't do that until you have a common denominator. So that's x to the 15/6 minus 5/6. What am I doing here? It's 2/6, sorry, 2/6. And then this is going to be x to the 13/6. This is the problem with making these videos late at night. I start to get tired. So that is it for A and B. And, you know, this one is, again, looks like it's challenging, looks like it's going to be really tough, but it really isn't that bad. Remember, this is raised to the 1/3 power. So if you start to rewrite this, this is the 1/3 power. And then you have this 6th root of x, which is the 1/6 power. So this is x to the 1/6 raised to the 1/3, and you're just a power raised to a power here. So this is going to be x to the 1/18 power. That's it. So again, it looked really tough, had a decent amount of shock value to it, but as you start to evaluate these, or simplify them, sorry, they're really not that tough. All right, so we'll do one more section tonight, and then we will call it, since I'm stumbling and pretty tired as it is, but yeah, we'll do these. All right, so 7.3, simplifying radicals, the distance formula, and we will skip the circles part, so we don't need to do that, but we will talk about the radicals and the distance formula. Okay. All right, so this says, as long as the indexes are the same, so n here, you are allowed to just multiply whatever the radicands are. Keep the index the same, don't change it. The reason why you were able to multiply A and B together is because the indexes were the same. If they weren't the same, then you would have to change them so that you could force them to be the same. So don't change the index if they're already the same, okay? That's going to be very important going forward. So you look at these and you say, I'm taking the square root of 5 and the square root of 13. That's just going to be the square root of 5 times 13 is 65. Easy peasy. Over here, I have the square root of 7 times the square root of x times y, which is just going to be the square root of 7 times x times y. So again, if the indexes are the same, it's just as easy as multiplying whatever it is that you have. Cube root of 2 and the cube root of 7 is going to be the cube root of 14. The 5th root of 9y squared x times the 5th root of 8xy squared is going to be the 5th root of 9 times 8 is 72. Y squared times y squared is y to the 4th, and x times x is x squared. Again, the order doesn't matter. Over here, 6th root, again, is going to stay the same. 8 times 2, 16. R squared, r to the 3rd is going to be r to the 5th. When you're multiplying like bases, add the exponents. This is where things get a little bit hairy because this is a 2. Remember, it's a 2 out of 1. This is a 3. So we cannot just multiply these until these indexes are the same. So what I usually do is, instead of writing this in exponential form, which is what I showed you before, is I can just quickly find the LCM between these indexes, and then whatever it is that you multiply to get that LCM, make sure that you raise these to those powers. So the LCM is going to be 6. So both of these should be 6. You have to multiply this by 3 to get 6, so this is going to be 7 to the third power. You had to multiply this 3 by 2 to get 6, so this is going to be 5 squared. And then if you're simplifying this, this is the 6th root of 5 squared times 7 to the third power, and I'm sure that you can figure out what those values are, but we don't really need to do that. All right, so this I said to you earlier today, I said we're going to learn a rule that allows you to divide and conquer. We had that big square root that I said it's easier for us to just take whatever the root is of the numerator and then whatever the root is of the denominator to figure out what the results are. We didn't know that this was a rule, but now that we do, we can use it. So we have this quotient rule for radicals. It's going to be pretty neat for us to do. All right, so again, this is just going to be the square root of 100 over the square root of 81, which is going to be 10 over 9. Over here, square root of 11 over the square root of 25, which is the square root of 11. I have no idea what that is. Wink, wink, wink. And then square root of 25 is just 5. So this right here is fine. It says assume that all variables represent positive real numbers. It says simplify. It doesn't say evaluate. So you should not be writing any decimals here. You're just simplifying this. And this is exactly what they wanted us to do. Okay. Over here, we are going to, again, take the cube root of 18 and the cube root of 125, which the cube root of 18 is just the cube root of 18, and then the cube root of 125 is 5, so we're done. So one thing that I want to mention now, we'll talk about this in the next video next week probably, is if these were reversed, if you had the square root of 25 over 11, this becomes a much bigger problem for us because at some point we're going to learn rules, conditions for a simplified radical. And one of the conditions for a simplified radical is that you cannot have a radical in the denominator. And since we have a radical in the denominator, we are going to have to what's called rationalize this fraction, which is to get rid of this radical in the denominator. We don't have to worry about that right now, but I do want to warn you that this is, I can't spell, this is coming, all right? So just make sure that you are aware of what's going on in this problem and how this is much more problematic than what we have over here. All right, so conditions for a simplified radical. Apparently it's right now. All right. Ooh, there's my watch. It's doing it again. So the radicand has no factor raised to a power greater than or equal to the index. Okay, so what does that mean? It means that you cannot have this. Let's say we have an index of 3 and we have x to the 10th power. This is a problem. This is violating the conditions of a simplified radical because it says the radicand has no factor raised to a power that is greater than or equal to the index. So we're going to have to fix this. All right, I'll show you how to do that. I'm not going to do it right now. I want to go over these conditions first. 2, the radicand has no fractions. So the second issue that you're having here is that if you had, let's say, the square root of, we'll go back to what we just saw, the square root of 25 over 11. This is a fraction. This is a radicand. It says you cannot have any fractions as the radicand. So you've got to fix that by, again, dividing and conquering. This is leading to another problem for us, okay? No denominator contains a radical. So this is exactly what I was just saying. You cannot have a radical in the denominator. We don't know how to fix this yet. I will go over this at a later time with you. But that is a condition that we are going to have to fix at some point. And then last but not least, exponents in the radicand and the index of the radical have a greatest common factor of 1. So one of the errors that you'll see is that it doesn't have this situation where this is a bigger number than that, all right? But they don't have a GCF of 1. So let's say I have an 8 here and I have an x squared there. So this is not greater than or equal to that. So that's not the problem, but their GCF is not 1. So one of the things that you can think about is that if you wrote this in exponential form, this would be 2/8. And you've learned, as soon as you learn fractions, you were taught that this is not simplified. You have to simplify this fraction. So this would become x to the 1/4 power. And now they have a greatest common factor of 1. So this would be the 4th root of just x to the 1st power. All right, so these are the 4 conditions of a simplified radical. Definitely get to know them. I'll try not to dive too deep into these tonight, but we'll definitely talk about a couple of them initially. Okay. All right. So let's take a look at this guy. So the square root of 32. So this is violating one of the conditions of a simplified radical because one of the factors of 32 is, of course, 2. And the other factor of 32 that is important to me is 16. The reason why I broke it up this way, because of course you could break it up as to 4 and 8. You can do, a couple of other ways as well, 32 and 1, which doesn't really do much, but that's another way to break up 32. So 2 and 16 is important because we can now take the square root of 16. So when you take the square root of 16, you get 4. And then you have the square root of 2. So that is the simplified form of the square root of 32. So for those of you guys who remember high school geometry when you were doing the Pythagorean theorem, this is ringing a bell to you. This is something that you focused on when you were learning the Pythagorean theorem, definitely. Over here, same thing. We've got 3 and 100 because 3 times 100 is 300 and 100 is a perfect square. So we can take the square root of 100. So that's going to be 10 radical 3. Over here, it doesn't matter how you break this up. If you break this up into 35 and 1, obviously that doesn't do much. 7 and 5, there are no perfect square factors of 35. So this is already simplified. There's nothing to do there. Over here, we're not looking for perfect squares. We're actually looking for perfect cubes. So how I would break this one up is I would break it up into the cube root of 27 times the cube root of 2. Because again, the cube root of 27 is going to be 3. And then you have the cube root of 2. So that would be your final answer there. Okay. Over here, I would do the 4th root of 81, and then the 4th root of 3, because 81 times 3 is 243, and the 4th root of 81 is 3, and then you cannot take the 4th root of 3, all right, without getting a decimal. Again, it's not asking you to evaluate these, it's asking you to simplify. So make sure you're not putting any decimals down. All right, I think this is probably a good place to stop for us tonight. We'll do these last 2, and that will be it. So again, this is the square root, right? And this is violating that property that says that the exponent here cannot be bigger than that, all right, than your index. So what I usually have students do is I have them break this up into a couple of different problems. I have them do the square root of 25, and I have them do the square root of p to the 7. And the square root of 25 is easy peasy. That's just going to be 5. This is where the problem happens, okay? Over here, what you could do is you can break this up so that it is a radical that has an exponent that is divisible by our index. Because right now, 7 is not divisible by 2. So it makes it a little bit trickier for us. So we break this up so that we force our exponent to be divisible by our index. So we make a p to the 6th, which is the largest exponent that I can have that is divisible by 2. And according to our exponent rules, that leaves us with a lonely p to the 1st over here. because p to the 6th times p to the 1st is p to the 7th. So again, I'm just rewriting the way that this thing looks. So it started off as the square root of p to the 7th, but now it's the square root of p to the 6th times the square root of p to the 1st. And we can apply that rule that we learned earlier, which says take this exponent and divide it by your index. And that's going to give you p to the 3rd power. And then there is nothing that you can do with this. So it's the square root of p. And I'll write it down here a little bit cleaner as a final answer there. Okay. So over here, we'll do, again, something very similar with different values. So we'll do the square root of 72. We'll do the square root of y to the 3rd. And we'll do the square root of x. So over here, we're looking for the largest perfect square factor, which is 36 times 2. The square root of 36 is 6. And then the square root of 2 is just 2. Over here, we break this up so that it's y squared and just a y, because y squared times y is y to the 3rd. This is just y, because the square root of y squared is y, and then the square root of y is just the square root of y. And then when you're taking the square root of x, that's just the square root of x, so there's nothing to do with that. And now once you have this, we want to just figure out what belongs on the inside of the radical, a 2, a y, and an x, and what belongs on the outside of the radical, this y and this 6. So our final answer is 6y, the stuff that's on the outside of the radical, and then the square root of the 2y and x. And that, ladies and gentlemen, is it for tonight. So I hope that you kind of followed everything that was going on in these videos. I know that it's a little bit tricky to show you how to do things on a calculator if I can't actually show you, and there's no point in me trying to find every single calculator that's in existence and try to model it for you. So if you're having issues typing these into your calculator, please make sure that you reach out to me so that we can fix it. Okay. So thank you very much for your attention, and I will see you all tomorrow.